Good day, everyone. We are from the Department of Statistics of the CUHK. Welcome to this engaging presentation on the fascinating topic of derivative and shape of graphs. Throughout this presentation, we will delve into how the derivative can provide us with valuable insights into the properties of a graph. Let us begin with an intriguing introduction. In the previous chapter, we discovered how the derivative allows us to pinpoint the absolute minimum and maximum values of a function. However, the derivative holds much more information about the graph, shedding light on various aspects of its behavior. In this chapter, we will embark on a journey to explore the concept of increasing and decreasing functions. We will delve into their properties, graphical representation, and theorems to test for them, unraveling the mysteries hidden within graphs. Now, let us transition to our first section, which focuses on the captivating concept of increasing and decreasing functions. Increasing and decreasing functions are like the yin and yang of graphs. They represent the upward and downward movements as we traverse from left to right on the x-axis. These incredible functions are also known as non-decreasing and non-increasing functions. To truly grasp their meaning, let us dive into the formal definition of these fascinating functions. Please direct your attention to the definition displayed on the screen. Suppose we have a function, denoted as f, defined on an interval I. Now, let's consider 2 points in this interval, x sub 1 and x sub 2. Here's the crux. F is strictly increasing on I. If, whenever x sub 1 is less than x sub 2, f of x sub 1 is indeed less than f of x sub 2. On the other hand, f is strictly decreasing on I. If, whenever x sub 1 is less than x sub 2, f of x sub 1 is greater than f of x sub 2. We also have the concepts of increasing and decreasing functions. F is considered increasing on I. If, whenever x sub 1 is less than x sub 2, f of x sub 1 is less than or equal to f of x sub 2. Similarly, f is considered decreasing on I. If, whenever x sub 1 is less than x sub 2, f of x sub 1 is greater than or equal to f of x sub 2. Now, let's witness how these definitions come alive when translated into graphical representations. Feast your eyes upon the captivating graphs displayed on the screen. In front of you are graphs that vividly portray the different types of functions we just defined: increasing, decreasing, strictly increasing, and strictly decreasing functions. The increasing function captures both strictly increasing intervals and intervals where the function remains constant. Likewise, the decreasing function comprises intervals where the function strictly decreases and where the function remains constant. If a function f, x, is differentiable on the interval a, b, and falls into one of the four categories we discussed, that is, increasing, strictly increasing, decreasing, or strictly decreasing, we label this function as monotonic on this interval. The concept of increasing and decreasing functions can also be extended to focus on a single point, x sub 0. In this case, we consider a small delta neighborhood that ranges from x sub 0 minus delta to x sub 0 plus delta. A function y equals f of x is deemed strictly increasing at x sub 0 if there exists a positive number delta such that for all x values within the interval, x sub 0 minus delta, x sub 0, f of x is less than f of x sub 0. And for all x values within the interval, x sub 0 plus delta, f of x is greater than f of x sub 0. We can apply a similar reasoning to define a function y equals f of x that is strictly decreasing at the point x sub 0. Moving forward, let's delve into the algebraic properties of increasing and decreasing functions. Observe the enlightening box of information displayed on the screen. Here's an intriguing fact. If we have two functions, f and g, both increasing on an open interval I, their sum, f plus g, will also be increasing on this interval. Likewise, if we reverse the scenario and consider the product of f and g, it will also be increasing on I. Similarly, if we take the opposite function, which is just negative f, it will be decreasing on I. Furthermore, if we consider the inverse function, denoted as 1 over f, it will also be decreasing on I. Now, let's introduce another exciting scenario. Imagine we have a function g, which is increasing on the interval a, b, while another function f is increasing on the interval c, d, with g mapping the interval a, b, to c, d. In this scenario, when we compose these functions, f composed with g, which is essentially the composite function y equals f of g of x, it will also be increasing on the interval a, b. Let us now venture into the next enthralling section, which revolves around the criteria for determining increasing and decreasing functions. To determine whether a function is increasing or decreasing on an interval, the key lies in examining the sign of its first derivative. Before we dive into the theorems that provide us with criteria for increasing and decreasing functions, let us take a quick moment to recap a theorem we encountered in the chapter on the mean value theorem. Fix your gaze upon the enlightening theorem presented on the screen. Let f be differentiable over an interval I if the derivative of f, denoted as f prime of x, equals 0 for all x in I, then it follows that f of x equals a constant for all x in I. Now, let's envision an interval, I, and define another interval, j, which consists of I minus its endpoints, if any. Suppose we have a function f that is continuous on I and differentiable on j. Given this context, we can take a deep dive into the following theorems, which provide us with criteria for increasing and decreasing functions. I present to you the theorem displayed on the screen. If the derivative f prime of x is greater than 0 for every x in the interval j, then it implies that f is strictly increasing on the interval I. The proof of this captivating theorem rests upon the application of the mean value theorem on the interval x sub 1, x sub 2, by incorporating the fact that f prime of c is greater than 0 and the observation that x sub 2 minus x sub 1 is greater than 0, we can conclude that f of x sub 2 minus f of x sub 1 is greater than 0. Consequently, this implies that f of x sub 1 is less than f of x sub 2. Now, observe the next thrilling theorem on the screen. If f prime of x is less than 0 for every x in the interval j, then f is strictly decreasing on the interval I. The proof of this thrilling theorem is reminiscent of the previous one, albeit with a slight twist. We utilize the fact that f prime of c is less than 0 and x sub 2 minus x sub 1 is greater than 0 to infer that f of x sub 2 minus f of x sub 1 is less than 0, indicating that f of x sub 1 is greater than f of x sub 2. Now, focus your attention on this captivating theorem. If f prime of x is greater than or equal to 0 for every x in the interval j, this implies that f is increasing on the interval I. The proof of this tantalizing theorem results from combining the previous two theorems we discussed. Now, let's examine the final theorem on this enthralling topic. If f prime of x is less than or equal to 0 for every x in the interval j, then f is decreasing on the interval I. Once again, the proof of this captivating theorem stems from the combination of the previous two theorems. To recap, consider the insightful box of information displayed on the screen. Let I be an interval, and let j be the open interval obtained by excluding the endpoints, if any, of I. Assuming that f is a continuous function on I and differentiable on j, then the following statements hold true. If f prime of x is greater than 0 for every x in j, then f is strictly increasing on I. If f prime of x is less than 0 for every x in j, then f is strictly decreasing on I. If f prime of x is greater than or equal to 0 for every x in j, then f is increasing on I. If f prime of x is less than or equal to 0 for every x in j, then f is decreasing on I. In short, we have learned how the derivative enables us to identify whether a function is increasing or decreasing on an interval. We have also uncovered various properties and criteria that can help us analyze the behavior of functions. By applying these concepts, we gain invaluable insights into the nature and characteristics of functions represented by graphs. In the last section, I will show you how to use the concept of derivative to analyze the behavior of some functions and their graphs. I will also give you some applications of derivative in economics and statistics. Let's start with the first example. On what interval is the function f of x equals x cubed plus x plus 1 increasing or decreasing? To answer this question, we need to examine the derivative of f, which is f prime of x equals 3x squared plus 1. We notice that, in fact, the derivative is positive for all values of x, hence f is increasing on negative infinity to positive infinity. You can see the graph of f on the screen. It is a smooth curve that goes up from left to right. The next example is similar, but a bit more challenging. Show that the function f of x equals x cubed minus 3x squared plus xx minus 1 is strictly increasing on the real numbers. To do this, we need to find the derivative of f, then we need to factorize the derivative as much as possible. We get f prime of x equals 3 times x squared minus 2x plus 2, which can be further written as 3 times x minus 1 squared plus 1. Now we can see that the derivative is always positive, because it is a product of a positive number 3 and a perfect square added to another positive number 1. Therefore, f is strictly increasing on the real numbers. The third example asks us to determine all intervals where the following function is increasing or decreasing. The function is f of x equals negative x to the power of 5 plus 5 over 2x to the power of 4 plus 40 over 3x cubed plus 5. To do this, we need to find the derivative of f, which is f prime of x equals negative 5x to the power of 4 plus 10x cubed plus 40x squared. Then we need to factor out a negative 5x squared from the derivative, and we get f prime of x equals negative 5x squared times x squared minus 2x minus 8, which can be further written as negative 5x squared times x minus 4 times x plus 2. Now we can see that the derivative has three zeros, negative 2, 0, and 4. These are the critical points that divide the real line into four regions: negative infinity to negative 2, negative 2 to 0, 0 to 4, and 4 to positive infinity. We need to pick test points from each region to see if the derivative is positive or negative. You can observe the diagram on the screen that shows the sign of the derivative in each region. Based on this diagram, we can conclude that f is increasing on negative 2 to 0 and 0 to 4, and decreasing on negative infinity to negative 2 and 4 to positive infinity. The fourth example asks us what is the length L of the interval on which the function f of x equals x to the power of 4 times e to the power of negative x is increasing. To find this length, we need to find where the function changes from increasing to decreasing, or in other words, where the derivative changes from positive to negative. The derivative of f is f prime of x equals 4x cubed minus x to the power of 4 times e to the power of negative x. We can simplify this expression by factoring out an x cubed times e to the power of negative x term, and we get f prime of x equals x cubed times e to the power of negative x times 4 minus x. Now we can see that the derivative has two zeros, 0 and 4. These are the endpoints of the interval on which f is increasing. The length of this interval is L equals 4 minus 0, which is 4. The fifth example is an application of derivative in economics. The profit function of acrosonic is given by p of x equals negative 0.02x squared plus 300x minus $200,000, where x is the number of acrosonic Model F loudspeaker systems produced. We want to find where the function p is increasing and where it is decreasing. To do this, we need to find the derivative of p, which is p prime of x equals negative 0.04x plus 300 equals negative 0.04 times x minus 7,500. The derivative has one zero at x equals 7,500. This is the critical point that divides the real line into two regions, 0 to 7,500 and 7,500 to positive infinity. We need to pick test points from each region to see if the derivative is positive or negative. You can see a graph of p on the screen that shows the sign of the derivative in each region. Based on this graph, we can conclude that the profit function p is increasing on 0 to 7,500 and decreasing on 7,500 to positive infinity. The last example is an application of derivative in statistics. Let x follow the exponential distribution with parameter lambda greater than 0. Then, the cumulative density function of x is given by f of x equals 1 minus e to the power of negative lambda x, where x is greater than or equal to 0. We want to find the limit of f as x approaches infinity, the probability density function of x, and the intervals where f and f are increasing or decreasing. To find the limit of f as x approaches infinity, we need to use the property that e to the power of negative lambda x approaches 0 as x approaches infinity. Therefore, f of x approaches 1 minus 0, which is 1, as x approaches infinity. This means that the probability that x is less than or equal to any large number is close to 1. To find the probability density function of x, denoted by f of x, we need to find the derivative of f, which is f of x equals lambda times e to the power of negative lambda x. This is the function that gives us the probability that x equals any given value. To find the intervals where f and f are increasing or decreasing, we need to examine their derivatives. The derivative of f is f, which is always positive, because it is a product of a positive number lambda and a positive number a to the power of negative lambda x. Therefore, f is strictly increasing for x greater than or equal to 0. The derivative of f is f prime of x equals negative lambda squared times e to the power of negative lambda x, which is always negative, because it is a product of a negative number negative lambda squared and a positive number a to the power of negative lambda x. Therefore, f is strictly decreasing for x greater than or equal to 0. You can see two graphs on the screen that show the shapes of f and f. This concludes my presentation on examples on derivative and shape of graphs. I hope you have learned something new and enjoyed this presentation. Thank you for your attention.